All right, hey everybody. So in this video and in several videos to come, we are going to really take a deep look at the idea of the curvature of a surface and measuring precisely how a surface curves in three-dimensional space. At the moment, we don't really have an understanding of this outside of the Gauss map, or the differential of the Gauss map, which we think probably plays a role. Otherwise, though, we have our ideas from curves, right? So we have the ideas of curvature and torsion, but we also understand that surfaces are more complicated than curves. They can curve in more interesting or more nuanced ways. And so we have to really think carefully about how to measure the ways in which a surface curves. And we're going to start in a very natural place with normal curvature. Before we do that, though, I just wanted to point out that there are definitely many different ways in which a surface can curve. And here I've drawn four different points, four different surfaces and four different points on these surfaces. And they're each curving in different ways. And this is language that we'll flesh out over the next few videos. But in short, on the far left over there, we have an elliptic point. And this is a point, it's slightly bowl-shaped, and the surface seems to be curving up in every direction, right? So it seems to be curving up in all directions. A hyperbolic point would be a point on a surface like this, right? And this is sort of like a saddle or like a Pringle of some sort. And you notice that if you travel in certain directions, it seems to be curving upward, right? So it seems to be curving upward here. But if we travel in these directions, it's curving downward. So it's curving up in some directions, down in other directions. That's a hyperbolic point. A so-called parabolic point is curling in one direction in one way, but seems perfectly flat in another way. And then finally, we have a planar point, right? And so a point that is planar seems like the surface isn't really curving at all, right? It seems perfectly flat near this planar point. And so clearly, each of these four pictures demonstrates slightly different behavior of our function. And our natural starting point, the so-called normal curvature of our surface, is going to be motivated from this rough idea of watching how our normal vector n changes as we move away from our point a little bit. For example, in this planar point that we're looking at, if I were to move away from this point, if I were to move around, my normal vector would continue to point straight up. My normal vector, though it changes its anchor point, does not change its direction. It stays pointing straight up. Compare that or contrast that to a hyperbolic point, where in certain directions my normal vector is moving this way, in other directions my normal vector is moving this way. So if we get a sense of how our normal vector changes as we move away from our point, we can get a sense of what our surface looks like. And that motivates this idea of normal curvature. Now, slightly more precisely, we are going to build on our understanding of curves to create this idea of normal curvature. So as our starting point, we are going to look at curves that go through the point we are interested in, right? And that lie completely on the surface, right? So if I have some sort of surface, I can look at a curve that's on the surface and goes through the point I'm interested in. And so we can imagine that because this is a curve in three-dimensional space, we can measure different properties of it, including its Frenet frame, T, P, and B, as well as the curvature and the torsion of that curve. So we have the capability of measuring all these different things about the curve, and then we're going to see what that tells us about the surface. And specifically, we're going to identify a vector, which we'll call the principal curvature vector, and we are going to see how much that vector points in the direction that is normal to the surface. So we're going to combine some of our theory that we've built up of curves with some of our theory that we've built up of surfaces. Just as a quick non-example, right? Notice in my plane here, right? Here's my plane. If I were to draw a curve that lies entirely within that plane and passes through this point, so let's say here it's entirely in the plane and it passes through that point, then this curve has itself, unit tangent vectors, unit normal vectors, all of that good stuff. And we could calculate the curvature of this curve, and this curve would have curvature, right? We would have a kappa that we'd be able to calculate. But that kappa, that curvature, would come from a principal unit normal vector, that is pointing still within the plane and does not point in the normal direction at all. So even though this curve lies entirely within the plane, I should say, yeah, even though this curve has curvature, it lies entirely within the plane and there is no normal curvature. There's really no curvature that's part of this curve that's pointing up in the normal direction. So that's all very hand-wavy, but that's sort of the idea that we're going to be getting at here. We can calculate the curvature of such a curve, and we can also figure out what part of that curvature points in the normal direction, and therefore actually is describing curvature of the surface, not just curvature of the underlying curve. So with that, let's take a look. Okay, so this is sort of my schematic that I'm looking at, right? I'm going to have a surface parameterized by a parameterization capital X. I have a point P that I'm interested in, and it comes from, in my parameterization, this point Q over here, right? So Q is mapping to P. At this point, I can construct a curve that lies entirely inside the surface and goes through the point P. And to do this, right, what I'll do is I'll actually draw my curve over here in my domain, right? So this is the curve alpha of t. It's this red curve over here. And then x of alpha of t is over here. That's the curve that I'm calling gamma of t. So this is a curve that lies entirely in the surface. It's coming from this parameterization. And if I want to examine this curve by itself, right, let me just draw it here off to the side. This is the same curve. Right, this is the same curve, but I'm sort of ignoring the surface for a moment and just looking at the curve itself. Well, if I wanted to examine this curve, I would find that it has, at every point, a given Frenet frame that I can calculate, right? So if I'm looking at that same point, I can calculate its unit tangent vector, I can calculate its principal normal vector, and I can calculate its binormal vector. And all three of these will be perpendicular to each other, right? So they will be orthonormal to each other. We can have our t, our p, and our b. And then we can also calculate the curvature and the torsion of this curve, right? So I could also calculate the curvature and the torsion at every given point. So for our, I should say, we have this equation for curvature, right? Where our t prime is equal to the speed times the curvature times our principal normal vector, aka if we took our vector t prime and divided by the speed, we would get this expression kappa times p. That's our curvature times our principal normal vector. And both of those expressions, right, or I should say either of those expressions, either this or this, are going to be the vector that I call the principal curvature vector. Right, so it's the principal normal vector to the curve that is scaled by the appropriate curvature kappa. And so both of these I'm calling the principal curvature vector. So in that case, I will define my normal curvature along the curve gamma at the point P to be given by this principal curvature vector dotted with the actual normal vector, capital N. And capital N, right, that comes from the surface, and that is the vector that is normal to the surface under this given parameterization. So that's my normal unit vector. And so here we have it in all of its glory. The normal curvature is going to be our principal normal vector dotted with, our principal curvature vector dotted with our normal vector, and I can write it in either form. So this is sort of a clunky definition, of course. It depends not only on the point, but also on the curve gamma, right? And so we could be concerned that different curves gamma that go through the same point might, and with the same direction, might give us different normal curvatures. And it turns out that as long as we have our curve going through the same direction, we'll be okay. So we have this fantastic proposition that says the normal curvature, kappa sub n, depends only on the direction that our curve is moving in. right? In other words, this is sort of our same schematic as before, right? Here's our point Q, which is our point P over here. Here I have my curve sort of floating in space by itself, just for illustrative purposes. And let's say that the direction I'm moving in here is this unit vector W, right? Then with this setup, maybe I should also say, to finish the setup, with this setup, I'm going to have my interval of time be such that alpha of 0 is equal to Q, and gamma of 0, therefore, is equal to P, and the unit tangent vector at 0 is equal to this unit vector W. So that's really defining the direction, right? This is a direction because it's a unit tangent vector, so it's really defining a specific direction that I'm moving in. Then with this setup, the normal curvature, as defined on the previous page, is just the second fundamental form of the vector W, which, as a reminder, is the dot product, negative dot product of W with the differential of the Gauss map of W. So what this is really saying is that the most important parts of my definition of normal curvature are not actually the alpha or the gamma, but it's really the direction W that I'm going through here. And any other curve gamma that goes through the same point with the same direction would have the same normal curvature. So that will make it much easier to compute normal curvature and will make it more invariant of the surface itself. Now, how are we going to prove such a thing? Right? Well, we're going to start with our definition of normal curvature, and then we're just going to try to compute as much as we can in sort of a follow your nose approach, right? So our normal curvature, as a reminder, was 1 over the speed of the curve times the dot product t prime dotted with n. Now what I'm going to claim is that we can move this derivative over to the other piece, right? And that in fact this expression will become negative 1 over the speed, and then it will be t dotted with n prime. So instead of t prime dot n, it'll be t dot n prime. And our trick for doing this is a trick that we've exploited a couple of times now, is simply going to be that if we have t dot n by itself, that is going to equal 0 because t is a tangent vector and n is a normal vector. Their dot product will be 0. And then I'm just going to take the derivative of both sides of this equation. The right-hand side remains a 0. The left-hand side has a product rule attached with it, so that's t prime dot n plus t dot n prime, right? And so all of those expressions, or those two expressions added together will equal 0. We just move one to the other side, and we get this identity here. So with that, I've rewritten my defined normal curvature in terms of this. And then I just have to figure out a nice way to express n prime, right? So if this is negative 1 over s prime and then t dot n prime, what is n prime? Well, let's look here in this red area, right, for these red equations. So if I want to figure out what n prime is, let's do a little detective work, find a nice way to write it. N of t, right, was really n of alpha of t, because n took as its input elements of the domain U. So n of t is really n of alpha of t. And alpha of t, to go back a slide, right, alpha of t is really u of t comma v of t, right? So alpha of t is defined over here in terms of its components u and v. Now, with that, we can see that n prime, calculating that derivative, will require a chain rule. And specifically, the multivariable chain rule says that we'll get n sub u times u prime plus n sub v times v prime. And at time 0, this just becomes, here I've just rewritten it and flipped it, that's u prime of 0 times n sub u plus v prime of 0 times n sub v, right? Now this is great because this could be realized as the result of the differential of the Gauss map, right? As a reminder, the Gauss map took in things like x sub u and spit out as outputs things like n sub u. right? And it took in an x sub v, output was an n sub v. So this n sub u is really the end result of a Gauss map, or differential of a Gauss map with x sub u. And similarly, this nv comes from differential of a Gauss map applied to x sub v. So we can rewrite this entire thing as the differential of the Gauss map applied to the corresponding vector in terms of x sub u's and x sub v's. And as it so happens, u prime of 0 x sub u plus v prime of 0 x sub v is exactly our velocity vector at time 0, which has speed s prime of 0 and direction w. In other words, it is exactly our velocity vector that is passing through that point in question at that moment in time with its velocity given by, or its speed given by this s prime of 0. So with that in mind, we now have a really nice way to write our our n prime, and we can take this and plug it back in to this piece right here. So what do we get as a result? Well, our normal curvature, right, which was this expression, can now be rewritten as negative 1 over s prime t dotted with this vector, this differential vector. And because the differential vector is linear, this constant can get pulled out front, cancel with that other constant, and we just get negative differential vector of w dotted with w, because, as a reminder, w is our unit tangent vector. It is equivalent to t, right? So our unit tangent vector, I should say at the point 0, at the point we're actually looking at, right? Our unit tangent vector is exactly the direction w. So what do we get? We get at the end of the day that all of this is just negative w dot dn sub p of w, and that was just how we defined our second fundamental form to begin with. So this is just the second fundamental form of w at p, which is fantastic. So what can we conclude from all of this? First, the normal curvature at a point p only depends on the direction w that the curve was moving in, right? So all of that other, stuff didn't really matter. It was just that direction. This also means that both k sub n and our second fundamental, kappa sub n and our second fundamental form are really measuring the same thing, right? And this sort of verifies what we had been claiming or what we'd been hoping would be true when we first introduced the second fundamental form, namely that it is measuring in some real sense how our normal vector n is changing as we move along our surface in a given direction, right? In this case, the direction would be w, and that's what we're plugging in here. Finally, right, now that we have this, we can imagine taking our calculation and finding our normal curvature in every possible direction, right? Now that all we have to do is come up with a direction w, we can look at a direction w and figure out the normal curvature in that direction. Look at another direction w and find the normal curvature in that direction. We can do this in every single direction, right? And on our surface, there will be a full 360 degrees or a full 2 pi directions we can go in, right? So going in all directions, we can understand how our surface is changing or just how curved it is in that direction by measuring the normal curvature.